All right, we got any questions before we begin today? No questions? So homework number 3 is going to be assigned today. It'll be due in 1 week. 1 week from now, we're going to have a review session. At least that's the plan for exam number 1. 2 weeks from now will be exam number 1 in class. Okay, so homework number 3 assigned today, going to be due in a week. And that one is not going to have, there's no chance for late submissions on that one unless you guys don't want to review it in the class, that review class. So make sure you hand that one in on time. All right. If there are, yeah. Yep. At least that's a plan for right now. It may be adjusted by like 2 days or something like that and be on a Wednesday instead. But yes, 2 weeks. All right. Any other questions? So let's just keep moving forward here. Last time we did first order systems. Today we're starting our second order systems. Right. So very obviously a second order system has a transfer function with 2 poles. We'll focus on second order systems without any zeros to start. But we could have up to 2 zeros, maybe even more technically, but we'll say 2 zeros. So we have a transfer function g of s is b squared over s squared plus as plus b squared, right? So as compared to first order systems, where could our poles be for a first order system or even our zeros? Where could they exist? What were they limited to? Only on axes, right? Specifically the real axis. I heard somebody whisper it in class too. You probably should have spoke up, right? Only can be real numbers, right? As compared to first order systems, second order, they have poles that can be real, they can be imaginary, or they can be complex, right? So now we're dealing with all 4 quadrants as well as the axes, right? And then we will have 2 exponentials that make up the natural response. Right? First order systems, their natural response had 1 exponential in there. This time we'll have 2. Well, in most cases, right? There will be 1 exception to that. So with exceptions. All right. So just like last time, we're going to focus on responses due to a unit step, right? And unlike with first order systems, they only had 1 type of response that you could have with a unit step going into it. Second order systems has different cases though. So there will be different responses, which will break up into different cases. Right. And so what we're going to be working with here, y is going to be g times u, right? Combining those 2 together, we're going to get b squared over s times s squared plus as plus b squared, right? And y as a function of time would just be that inverse Laplace transform. B squared over s times s squared plus as plus b squared, right? Inverse Laplace transform of that. right? So let's go through, was it 3, 4 cases? Yeah, 4 cases today. Just to review all our different responses here. So case number 1, right? What I'm going to do here is I'm going to choose different values for A and B. For this first case, I'm going to say A is equal to 0, B squared is greater than 0. Really, B is greater than 0 is what we're going to focus on, right? And we're going to say our poles of G of S, right? So how do we get our poles of G of S? What are they in this case? With A is equal to 0, B squared is greater than 0. What are our poles? What do we get? What do we need to get first to get the poles? Say again? Characteristic equation, right? What's the characteristic equation for a transfer function? Set the denominator equal to 0, right? So we're focusing on the transfer function for G of S here. So we're going to set S squared plus AS plus B squared is equal to 0, right? What do we get for our poles in this case? What are they equal to? S is equal to B. What do you guys think? This could be a quick class, guys, by the way. If you guys like participate in stuff like that, we could actually finish early today. BI or BJ is what I tend to use here, right? So this is S squared plus B squared is equal to 0, right? We're going to have a negative B squared. S squared is equal to negative B squared, right? So we take the square root of that, we're going to get an imaginary number in here, right? So we get P1 and P2 going to be JB and negative JB, or IB and negative IB, whatever you want to call it, but that's our imaginary number. All right, so if we were to draw this on our real imaginary axes, where would these poles exist? So we got imaginary poles in a pair, right? So where they exist? Right here, right? This is B, and that's negative B, or vice versa. I guess it depends on what B's value is, right? They would end up on there. Okay, so just hazard a guess. What is our solution for y as a function of time for a step response? Right? What do we think? And maybe it'll be easier to first just talk it out. If we were to plot it, what do we think y is going to look like as a function of time? Flat? Flat, but you're drawing a square. So you're saying like a square wave? Okay, so you're saying like a step square wave or something like that. Okay, it's one idea. Other ideas? Should still kind of be review for you guys here. What's the response look like? Well, it's only been what? Semester since you guys have taken 33, right? Maybe longer. We got one guess. Something like that. Yeah. Oscillating and approaches 0. All right, so getting closer here. Oscillating, I like that word. Approaching zero, not necessarily, right? So approaches B. Yeah, I think it's going to be, I'm not sure if it's going to be B. Let's think about it. Yes, I think it would actually approach, no, it approached 1 in this particular case here, but you're on the right track here. What it's going to look like, well, maybe it'll start out a little bit funky or something like that, but actually it would look something like this. A sinusoid around a constant, right? Remember, our responses are the free plus the forced parts, right? The forced thing, right? The pole associated with that is a constant, right? The other two free parts, right? Those are our two exponentials we talked about earlier. So y is a function of time, the inverse Laplace transform, b squared over s times s squared plus b squared, right? Since that a is equal to 0 here, right? We could use partial fraction expansion and all that sort of stuff. We would end up with C1, just a constant, plus C2 e to the j bt plus C3 e to the negative jbt. Our poles are the things that end up showing up in our exponentials, right? Right? What is this also equivalent to? Right? Somebody whispered it. It's something along those lines, right? It's going to be relating to a sine or a cosine, right? I'm just going to say a cosine bt minus phi here for one form of that, right? That comes from the relationship between exponentials with imaginary parts in them and sine waves and cosine waves and tangents, right? Right, that's what your Euler's formula, Euler's something. Yeah. You gotta say it louder. So you can either have cosine plus sine, right? Or you could have a cosine or a sine with a phase. Those would be two equivalent things there. There's another formula that allows you to trade between those, right? So you could probably write it out as a cosine bt plus b sine bt or something like that. That would be another equivalent solution to this, right? So anybody want to hazard a guess for the name for this case here? This is case number 1. What is this called? What kind of system is this? Phasor? All right, at least you remember that term, but I don't think so. Now I'm talking about the second order system in particular here. Along those lines, right? Undamped, right? This is an undamped system, right? The name can, I guess it sort of comes from mass spring damper systems, right? If you don't have a damper in a mass spring damper system, right? It's just a mass and a spring, right? And you put a step input into it or put just an initial condition into it. What's going to happen? The mass is going to move, transfer all that kinetic energy into potential energy. Then the potential energy is going to transfer back into kinetic energy for the mass, right? And there's no way to dissipate that. It's just going to keep oscillating forever, right? Assuming it's a stable or marginally stable system, right? And we end up with undamped effects, right? It's going to look like a sine or a cosine of some form, right? We have kinetic energy and potential energy. That's one way to describe this, just constantly exchanging between each other, right? All right, that was our first one. Let's go to case number 2 here. Now that you guys are familiar with what we're doing here, maybe we can get a little bit more participation. Let's now set b squared, or I'm just going to say b is greater than 0, which means b squared is going to be greater than 0. And let's say a is greater than 2 times b. So first thing, what are the poles of g of s? Right? We said before, let's just take our characteristic equation and we solve that. Now, last semester, when I taught this class, like, it felt like 90% of those folks really relied on like SimLab or something to solve this, right? Or something online, right? You guys, I'm sure, don't need that, right? How do we solve this equation? No, not Wolfram Alpha, because that's what I would do. What else? Say it. Sure, that's close enough, right? I would say just the quadratic formula, right? You guys know the quadratic formula from like 8th grade? You're going to do it a lot. So get confident at it now if you're not already. All right, use the quadratic formula. Tell me what our poles are. Can't believe I'm teaching a senior college level class and need to review quadratic formula. I'm gonna hope that everyone here knows what it is. Tell me what the answer is. Give me my poles, guys. What are the poles? Somebody else. Yeah, obviously, right? Okay. So we don't have like a ton of information, right? Like this does give us our poles, right? But what was our next step? I ended up plotting these on the real and imaginary axes, right? So where do these poles end up based off of those conditions? Where do you guys think these poles are going to be? On the real axis, okay. Complex. So you're saying complex if it's in the quadrants? But I gave you some ranges for A and B, right? So how about we use those? All right. So good. Depends on what A and B are, that's correct, right? And I started off by saying what A and B are relative to each other. Right? That's the key. One person said it right, but you guys literally said everything. So question is, who said it right? Why are they both on the real axis?
A squared is 4.
So let's look inside the square root, right? The square root is the only thing that could generate those imaginary parts, right? And make it a complex number, right? This part over here, that's the real part for sure, right? So we know A is greater than 2B. That must mean that A squared must be greater than 4B squared, right? Therefore, stuff in the square root is positive. So it's real, right? So we should end up with 2 real roots, right? 2 distinct real roots in this case, right? They can't be the same. They both should be on the left half plane, right? Not over here, somewhere over here. All right. So again, let's talk about that solution to YT for a step. What do you guys think it's going to look like in this case? Or maybe better, for some of you, you recognize what this case is.
P could be in the middle, or I guess. P could be getting closer to the camera.
Peak will be in the beginning, it'll decrease like this
No, that's.
as a sinusoid. Like that. What do you guys think? It's an idea. That's going to be one of them, but is it this one? What is this called? Maybe that'll help you guys. What's the name of this? This is overdamped, right? Parabola? Well, we're dealing with exponentials, right? We said that at the beginning, so maybe, sorta. It's gonna look something like that, right? Maybe it's going to be like two exponentials added together here, right? Maybe that's what you're thinking of here, something along those lines, right? Our solution, this one's probably the easiest one to solve, would just be C1 plus C2 P1T plus C3 e to the P2T. Right? Where those constants depend on what A and B are. So it is two exponentials added together. This one probably looks the closest like a first order system, right? This is our overdamped system, right? We have a lot of damping in this case. All right, let's move on to case number 3, unless anybody has any questions on case number 2 here. All right, that's overdamped. Now let's say B is greater than 0, which means B squared is obviously greater than 0. And A is going to be greater than 0, but less than 2B. Right? Now let's again talk about the poles of G of S. Right? What do we end up with our poles? Still the same like equation. Right? But what happens in this case? Say louder. Complex? Why complex? All right, so in the square root, we had a squared minus 4b squared, but a squared has to be less than 2b squared, right? That's what this is saying. But still greater than 0, right? So between these two things, in the square root, we get a negative number. All right, so we could rewrite our poles out. Right, where negative a over 2, I'm going to pull that out in front. And we're going to have plus or minus. I'm going to take the negative out of what's in that term there. So I'm going to have j square root of 4b squared minus a squared, right? That'll make it a positive number over 2. And these are our poles. We end up with complex numbers. Right? Complex poles with negative real parts. Right? The imaginary parts have the same magnitude, they're just the opposite sign, right? Those always come in pairs. So what do we end up with here? Real and imaginary. Where do these guys go? Right? They're just complex numbers, right? And they have negative real parts somewhere like here, right? They have the same real part. They're both negative, and the imaginary parts are flipped from each other. Right? Okay, so let's talk solution to YT for a step response here. All right, what's that one gonna look like now? What do you guys think? Right? So I think somebody answered this earlier. They were confusing overdamped and underdamped here, right? So we have some sort of constant value. I think it's going to be 1 for a steady state. We're going to start out. We're going to do that. We're going to oscillate 1 or multiple times and eventually flatten out. Yes.
Scroll up for a few seconds. Thanks.
Right. This is, what is it called? This is underdamped, right? Doesn't have a lot of damping, so we get a lot of that kinetic energy and potential energy exchanging between each other still, right? It's slowly dissipating, but not dissipating very fast, right? Our solution for this, you could still say C1, C2e to the P1t plus C2e to the P2t. But an alternative one, we C1 times something, I'll get into that in a second, times a cosine. Right, where we just have a whole bunch of constants in here, I'm not going to worry about. Right? So that cosine is decaying. At what rate is that cosine decaying? Or what kind of function would describe how that cosine decays here? What do you guys think? I didn't draw it to scale, so don't trust this, right? Is it linearly, just going straight down like that until it reaches steady state? Probably not, right? It's an exponential decay, right? So this is an exponential decay here, which means we would have an exponential floating in here somewhere. Right, we'll get into that more next time. Right, what's this called here? This first peak, where we miss the value that we're going for. Anybody recall the name of that? That's overshoot. Yeah, maximum overshoot. I just call it overshoot a lot of times, right? So this is our underdamped system, right? We are dissipating energy over time, but it's taking a long amount of time to do it, right? Because we don't have a lot of damping. We are underdamped. All right, last case study. All right. What is this one going to be named? This one's critically damped, right? Okay, so tell me, if B is greater than 0, to get a critically damped system, what do you guys think A should end up being? Was it?
It's equal to B.
2B. We'll find out why in a second here. We already did A is equal to 0, remember? That was our first case. That was the undamped system. So let's look at our poles of G of S. So what do we get? All right, you can do the quadratic formula here. That may take a little bit longer than you would need to. What was that?
Yeah.
B and minus B? Close, not quite.
Yeah.
B and B? Close, not quite. Try not do it in your head, unless you're really confident. What? Repeated root, and what is the value of it? Right? Negative B and negative B, right? Because this is S squared plus 2BS. plus b squared, right? You can actually factor this apart into two pieces. Right, so that's s plus b squared is equal to 0. So our roots would be negative b and negative b here, right? So we get repeated real negative roots. Right, or repeated poles, sometimes I would say. Right, so that means on our j omega and sigma axes are real and imaginary, we would get two poles that are kind of overlapping each other here, right? Two poles that are at the same exact value. Right, we said already the name of this system is critically damped. Right, and what is that step response? Right, what do we think it's going to look like in this case? Think it's going to oscillate for a short time? Maybe not close, but not quite. So that's what he's arguing. So what do you guys think? Is there overshoot of any amount with a critically damped system? Very little, so much that it is 0. It is perfectly 0, right? Critically damped. So we've gone through the math here, right? It is the border between underdamped and overdamped. Overdamped doesn't have overshoot, right? Underdamped definitely does, right? Critically damped is pretty much as close as we can get without having any of those kind of like dynamics existing in our system here, right? So what do we think the response is going to look like? Let me draw. This will be let me try again. This is overdamped here. So how do you guys think critically damped is going to look? Yeah. Right. So if I drew this or I drew this, which one? Second one I drew, right? Critically damped would look something like this. Right? This is critically damped. Now, before I said there's an exception to our solutions, right? Critically damped is our exception. We're going to have C1, right? Just like constant. Again, these constants depend on A and B. C2 times T, E to the PT, right? Because our poles are the same, plus C3, E to the PT. So we have two exponentials, right? But one of them also gets multiplied by time, right? And that has to do with going through the inverse Laplace transform for a second order system that's critically damped and undergoing a step response here, right? Any questions on critically damped? Is critically damped the fastest way to get to your steady state value? How many hands say yes? No? All right, I guess we'll find out a little bit later. All right, so they happen at the same time. Clever. Not quite. So let's just summarize all this stuff up here, and we'll do a couple examples, and that'll be it for today. So, name, and then I'm going to say our identifier for now, even though this will change by the next class. Right? You guys should be able to see a pattern with our poles as it relates to these different types here. So we had undamped, right? We had underdamped. We had critically damped. And we had overdamped. Right? how were we able to tell the difference between these guys? Based on the roots, right? So choose one of these categories here and tell me what was unique about their roots. Preferably from someone I haven't heard from yet. Online or in person. Prickly damp was repeated, right? That's probably the easy one to go with since we just covered it, right? So we have repeated real negative poles for G of S. Okay? What's another one? Add imaginary poles for G of S or of G of S. Right? What are the other two? Real negative poles, not repeated, right? For G of S. And then underdamped, complex poles with negative real parts. Right. I see folks in the chat also got that covered too. Right? So, going off of what we did here today, right? You guys notice a pattern relating maybe those oscillations that we had in our poles? When did the oscillation show up? When our poles had what? It wasn't just complex. When we had some amount of imaginary, right? Either complex or pure imaginary numbers, we had oscillations in our system, right? Imaginary numbers in our poles relates to oscillations. Keep that in mind. Right? Also note, numerator of G of S doesn't really matter here, right? Input doesn't matter either. When we're categorizing a second order system, at least for our open loop plants right now, we're just looking at the poles of G of S of our transfer function, our plant itself, right? Okay, couple examples to wrap up today. I want you to just determine the type of second order system for the following transfer functions. First one, G of S is equal to 15 over S squared plus 9S plus 8. And then our second one is going to be G of S is equal to 22S plus 5 over S squared plus 6S plus 20. And that's it for today. So just tell me, which one of these do they fit into? What category? Go. Let's give people some time to work on it though. Let me put it this way. If you want to take off, if you got them right, or I guess even if you just gave up, we're done for today besides this, right? If you want to come up and double check with me, you're welcome to, or I can come to you. Probably not for the people in the middle there, maybe towards the end of the class here. But this is it, right? I can give you guys like 5 minutes or so, and then we can go through them very quickly. But this is it. So if you want me to go up there and check, is that what you want? No, you're good? All right, this is practice for you guys. You can simplify this way more, make this more complicated than I think it needs to be. Right? Do you see what I'm saying?
I always.
Do you want to rewrite that as S plus something? That's S plus something? What would it be? Say if you want to separate factor,
Oh,
right? Wouldn't that be way faster for that?
yeah.
Yeah.
I mean, I kind of just. This part is. Not negative.
Yeah, it could shift it to be a positive number though, in some cases, not in this case. But what I'm saying is the input one of the 8 negative 1 and
Oh,
8, right?
yeah.
Just factor that, right?
Yeah.
Say you took the long way for this one, it was not a clean number.
Yeah.
Where you definitely need to. That one looks like you have the right procedure and carry. That's what I'm trying to point out, right? Save yourself some time. Positive or negative? Right, very critical. Oh. Don't skip things unless you're 100% sure how to do. Is it be positive or negative? So it's S plus 1 times S plus 8, which means they're both. This one, I don't think it comes out to be that simple. But it is underdamped. Does it really come out to be 2 times 11? I'm not sure about that, but this answer is right. You may want to just double check.
Yeah, I guess we can keep maybe under.
Look at these rights.
Either under them.
Yep.
Or expression over there.
That one I'm not sure about. Is it, does it simplify that much?
Yeah, I do last week, I divide 6.
Yeah. Okay, it does. Yeah.
And that is,
So that's why I'm actually looking for these problems, so make sure.
Yeah, but just for the place on.
Yeah. Right. Yeah, you got it.
They have a real. Negative.
Yeah. That's
Zeros do not impact if it's under damped or over damped or critical. Zeros have nothing to do with it. It's only the poles. Good question. All right, I'm gonna shut down the recording and everything here. If anybody wants to get some help, I'll still be here for a couple more minutes. Let's stop the recording here.